I think we can get started. So let me maybe tell you firstly a bit about my background and why I'm telling you all of this. So my name is Kristaps, and so I graduated from Tallinn University of Technology in engineering, and I have been working with SPH engineering and with UGCS since 2014. So this year is going to be already 6 years. I'm also a licensed pilot for drones here in Latvia, and I'm licensed to fly UAVs up to 25 kilograms. And also in 2019, so in summer of last year, I participated in the expedition in Greenland, where we were searching for a lost Grumman dog aircraft using GPR. Unfortunately, that year we did not find the aircraft, but later in the webinar, I will show you some data from 2018 when we actually did find a Lockheed Martin fighter from World War II in Greenland. So, okay, I think let's move on further. So I think firstly, I'll just cover some kind of basics about how a GPR works, what are the basic working principles. I guess some of you probably already know this, but I think it's still kind of good to cover this, and then we will move on further. So firstly, the way a GPR works is in many ways similar to echolocation. So basically, on a GPR, there is the transmitting antenna and there is the receiving antenna. So essentially, it's sending electromagnetic pulses through the ground, and then it's measuring the time it takes for the wave to reflect back. And in different mediums, so let's say if you're using GPR over soil or over normal soil or over sand or over water, then this time it will take for the electromagnetic wave to travel through it, it will be different. And so this kind of also tells you how deep can you see in different mediums. This I will cover a bit further in the webinar. Also, what's important is the two-way time. So this is basically the time it takes for the wave to travel to the object and then travel back. So essentially the GPR is kind of listening for how long does it take for the wave to bounce back. And also this is kind of how it is measuring the, how it's measuring whether there are any objects or not. Also, I'll touch upon the subject of frequency, because basically there are some GPRs with higher frequency and some GPRs with lower. The kind of rule of thumb here is that with higher frequency radars, let's say 500 megahertz, you are not able to penetrate as deep, but you are able to see smaller objects. Whereas with some lower frequency radars, such as the ones made by a radar team, with these you are, let's say, I think there's some with center frequency of 124 megahertz. I'll show it to you exactly once we go on further. But with these, for instance, you can see a bit deeper in the ground, but however, you might not be able to detect small objects such as pipelines. So for this, you need a different radar. So always, when you kind of want to understand what radar would be best for your purpose, you need to kind of consider what frequency is it, and this and kind of what size of an object can find, and this is kind of how you find which is the best radar for your application. And regarding applications themselves, there are quite a few. So GPRs can be used in fields such as archaeology for finding buried structures underneath the ground. We are also experimenting with using them for landmine detection. They can be used for groundwater prospecting, snow and ice profiling, a few others. Also, higher frequency radars such as 500 or 1000 megahertz, these can be used for utility detection. So this means detecting cables, detecting pipelines. Also, you can use these actually for forensics, for mining industry, and various other industries as well. One other quite important thing that's worth mentioning about GPRs is that there are a few limitations. So firstly, it is not possible to use GPRs over salt water. So for example, if you're going to be flying, if you want to fly over, let's say, a beach near the ocean, you're probably not really going to be able to find anything using the GPR simply because the data is going to be full of noise, and this is due to salt water. Secondly, also, if the soil has a clay layer inside of it, then you will be able to see the clay layer. However, you will not be able to see anything beneath it. So the clay, in a way, it can act as a shield. So this is also one of the limitations. And secondly, regarding the object types. So from GPR data, it is kind of possible to tell that there is some sort of anomaly inside of the ground. However, you can't say exactly what it is. Let's say if there's some buried car in the soil, you're not going to see like an image of a car from the GPR data. You're simply going to see some reflection from an object, and you'll kind of have to judge how big the object might be, what's the depth of the object, and then you can kind of investigate it further in many cases by excavating to understand if it is indeed something unnatural or not. So about methods of GPR, there are a few kind of conventional GPR methods. So these include using a GPR on a cart. These also include towing a GPR behind a vehicle, let's say just towing it behind a truck on the same cart. Also, you can use GPR as a handheld device simply by walking with it. And also for some applications such as bathymetry, you can also use GPR on a boat. What I want to kind of mention and also put an emphasis on is that using a GPR on a drone, what we are doing, this isn't really a replacement for conventional methods. It's simply an additional method that you can use to perform GPR surveys. And this is why actually the antennas that we support, they can be used either on a drone or actually using some other method. So let's say, because one of the main limitations of using GPR on a drone is that you lose a bit of the penetration depth. And essentially, once you find an anomaly with the drone, then in many cases, it's worthwhile to actually scan this anomaly once again by using the GPR on, let's say, a cart. So of course, using a GPR on a drone, there are quite a few advantages to this. So firstly, you get higher survey accuracy. So when the drone is flying in automatic mode, it's able to keep its speed and position quite more accurately compared to a person driving a vehicle or simply pushing the GPR on a cart. Also, this actually increases your productivity because you can perform the surveys a lot faster and again, with a higher degree of automation, since obviously the drone doesn't really get tired, you can simply make the mission for it and it will fly it until the battery runs out, which you will simply change. Another good feature of using GPR on a drone is the fact that it does mitigate the risk for personnel. So when you're using GPR in some situations, it is actually dangerous for people to be there. One example would be performing snow profiling. And this is something that we also did during the Greenland expeditions, where we simply have to find the depth of the snow layer. So in places where the snow layer is quite a few meters, it is very dangerous for people to be there. However, with the GPR, with the GPR on the drone, that's not a problem really, because it doesn't obviously need to touch the ground and no one needs to be close to it. So this is why in those cases it is better. Also, of course, it's in some cases it can be more cost efficient because as you're saving time to perform it, then also this kind of does translate to cost savings. So if it takes less time for you to scan a certain area, then you save time, and this is how it also leads to cost savings. Another case would be using GPR on uneven terrain. So if you're using it on uneven terrain, it might be quite difficult for either a person or a land vehicle to go through this. However, with an airborne GPR system, it is not really a problem and it can handle that without an issue. So of course, it's also worthwhile mentioning some limitations of using GPR on a drone. So one of these limitations is the weight. So you have to always consider how much does a radar weigh. We have a few radars that we support made by Radsys and radar team, and they weigh up to about 4 kilograms. I think 3.5 is the heaviest, if I'm not mistaken. And most industrial drones have a payload capacity of about 5 kilograms. So this means that heavier radars, especially those with lower frequencies, they cannot really be used with drones unless perhaps you're using some heavy lifting drone. Then next is, like I already mentioned, that you do lose a bit of penetration depth when you're using the GPR on a drone. Actually, in quite a few cases, it is about 2 times the penetration depth that you are losing. And further on, I'll show you a table where you kind of see what is the, how deep can you see with the GPR when you're simply using it on the ground, and how deep can you see with the GPR if you are using it on a drone. Another argument would be the limited flight time. So obviously with the drone, you can't fly forever, especially with normal electric drones. So these you can go up to about 15 to 20 minutes with carrying the GPR. And then of course the batteries will need to be changed. With UGCS software, this is not really an issue because we support restarting the mission from the last point. So simply you need to change back with the drone, you need to come back with the drone, change the battery, and then you can continue. But there are some alternatives such as using a hybrid drone. So if a drone has a petrol engine on board, so it basically acts like an onboard generator, then it can give you a flight time of even a few hours. And this kind of takes this limitation away. Another thing to consider is that with a GPR on a drone, you do need to perform the flights at somewhat of a low altitude. And this is why we also have the terrain following on our drones. So here I have actually in the background here, if you can see, I have the M600, and on this we have the laser altimeter. I will tell you a bit more about all the components of our system, but this is kind of what allows you to fly a bit lower than you would without it. So as an example, with a 500 megahertz antenna, which is what I have here, you normally fly with the terrain following at, let's say, about 1.2 meters. And this means that the height between the antenna and the ground would be about 60 centimeters. Although this is actually about the limit, so maybe from 60 centimeters to, let's say, 1 meter, this might be the flight height of the antenna. Another kind of thing that's worthwhile mentioning is that for the drone, obviously you do need some space. So in some tight places, let's say, as for example, city streets, it might be a bit more difficult to use the drone, especially if they're quite narrow. So this does take away this use case. However, on more kind of wide open areas, this isn't really a problem, and same goes for places where you don't need to be where you can place the drone basically at the larger distance between you. So this can also help. So here I have basically a comparison of antennas that you can use with our GPR system. So basically there are 4 main antennas that we currently recommend. So they're either made by Radsys manufacturer, which is also located here in Riga in Latvia, or made by a radar team, which are located in Sweden. So the center frequency, as you can see, it goes from 1000 megahertz to 80 megahertz. And so this also does affect the penetration depth from surface. So penetration depth from surface, this means that assuming a case when it is not mounted on a drone. So you can see here with the 1000 megahertz antenna, you can see from 1 up to 2 meters. Then as you move on to a lower frequency, you can see from 4 to 10 meters. And then as you move on to even lower frequency, so going from 500 megahertz to about 124 or 80 megahertz, then you will be able to see deeper. So let's say 15 to 20 meters or 20 to 40. But of course, by using a lower frequency antenna, you will basically lose the resolution. So this means that you will not be able to detect smaller objects. And also actually here, you can also see the penetration depth from the drone, the penetration depth from the GPR when it would be mounted on the drone. So for the 1000 megahertz antenna, it's actually quite low. So it's from 0.3 to 0.5 meters. Obviously, this does depend on over what soil you're flying. And then again, for the zone 500, then you can see it's from about 2 to 5 meters. So this is basically about, you can lose 2 times the penetration depth compared to using the GPR simply on the surface. Also, of course, there's the maximum distance between the antenna and the surface in airborne surveys. And so with higher frequency antennas, you want to be as low as possible. So with the zoned radars, basically, you want to be about 0.6 meters. That should be the distance between the antenna and the ground. So I'd say like 0.6 up to 1 meter in most cases. And with the radar team Cobra, you want to be a bit higher. So this can be about 2.5 meters up to 3.5. Yeah, and lastly, there's the minimum size of detectable object that you can detect from this altitude. So, for example, with the 1000 megahertz antenna, you can detect an object of about 7 centimeters. So this actually makes it somewhat suitable for some old landmine detection. And then as you move on further, you can see let's say with the radar team Cobra radar SC150 with 124 megahertz center frequency. With this, the minimum object you can detect is 40 centimeters. So this means that you won't be able to detect smaller objects. You won't be able to see some pipelines. So this is what you always need to consider when you are choosing your radar. And if you want to use the radar for quite a few applications, I think then maybe there might be like a good middle ground, which would be the 500 megahertz zone, because this you can use for detecting some smaller infrastructure, and also you can use this for maybe detecting some larger objects which are a bit deeper underneath the ground. But again, always you need to consider what is the exact application and what target do you want to detect. So I think now I will kind of explain a bit about the components of what we have within our GPR system. So firstly, obviously we have the drone itself. So in this case, it's the DJI M600. And then, of course, we have the ground penetrating radar. In this case, as you can see, I have the 500 megahertz rad-zone radar mounted underneath. Then what we also have in our system, we have the data logger, which is called SkyHub. So in this case, it is located right here underneath the drone. And so the data logger, it's basically responsible for firstly logging the radar data during the flight. So this data isn't saved on the computer during the flight, it's saved on board the drone. And after the flight, you're simply downloading the data. And also, when you are using the drone with terrain following, also this data logger is what kind of helps you to achieve this flight altitude that you have set. So basically, it controls the drone's flight as well. Then also we have altimeters. So we have on this drone, actually, we have mounted both. So we have the laser altimeter as well as there on the back of the drone. It's probably a bit harder to see, but we also have the radar altimeter. So these altimeters are what you are using for terrain following, and this basically allows you to avoid using the barometer and basically fly according to the data that you get in real time. And then, of course, there's the software part. So regarding software, we are using our own UGCS flight planning software, along with one other software component, which is called the custom payload monitor. So this is basically responsible for communicating to the data logger. And I will demonstrate the software to you as well as we go a bit further. So I think now might be the time to actually do that. So let me switch the screen sharing. So 1 second. Okay, so here you can see our UGCS flight planning software. Let me put this a bit to the side, and I will also open up our custom payload monitor. Let me move the zoom controls a bit out of the way here. Okay, so this is basically what you would be using during the flight. So firstly, we have the UGCS flight planning software, and then we have the UGCS custom payload monitor, which you would use to control the true terrain following as well as to see the radar data. So firstly, let me just add a drone here. I think I will just add an emulator drone. Let's remove this one. So here, as you can see, we are seeing the telemetry from the drone. We have the commands that we can send to the drone. And then, so basically in UGCS, everything that is on the right side, this is concerning the drone control. So you see the drone, you see telemetry as well as commands, and everything that is on the left side is regarding mission planning. So now I'll just attempt to create a mission for simply a sample mission that you can use with the GPR. So we can choose this area, for example. And then let's just click on add new route, and then I'll create a new route from scratch. So let's assume our drone is somewhere over here. The emulator drone will simply jump to this point when we start using it. So I'll just put one waypoint here. I'll just change the altitude of the waypoint to, let's say, 5 meters. And then I will add an area scan tool. So you can see in the area scan, we can define the flight height as well as the side distance explicitly. In most cases, when you're flying with a GPR, you want the side distance to be, I'd say, probably less than 2 meters. In this case, let's use a side distance of 1 meter, and let's use a flight height of 5 meters, for example. But it's important to note that this altitude that I'll be setting here, it will actually be overridden once we start true terrain following. So this is simply for kind of previewing purposes. And then once we start, then the drone will actually move lower according to the true terrain following. So here, let me simply create this kind of area scan. I'll also change the direction angle of the survey lines. Let's maybe adjust the shape just a bit. This area actually might be a bit bigger than it seemed at first, so let's maybe move it just a bit closer. Okay, so once our route is calculated, I will also add another waypoint that will bring the drone back to the launching position. Let me just expand this here, and then I will also add another waypoint over here. Okay, so now you can see we have our initial waypoint, we have our area scan mission, and we have our last waypoint. Normally, also at the very first waypoint, I will be adding a wait action, and this will allow us to switch into terrain following mode. So let's add the wait action as well. So let's say we can add the wait of, for example, 5 seconds. Then we have the area scan, and then we have the last waypoint. I think also here I will switch to a bit of a lower flight speed, but again, keep in mind, this will be overridden once you go into terrain following, but still, if in some case it will not be overridden at the very start, then the drone will not fly as fast. So I just prefer to kind of set this to a bit of a lower value. And when you will be doing your terrain following, in most cases, it's recommended to fly with speed ranging from 1 meter to 3 meters per second, not faster than that. So flight speed is 2 meters and flight height is 5 meters. I saw there was somewhere a question about, are you able to fly with the antenna parallel to the ground? So essentially with UGCS, there are like 3 ways of how you can fly according to the ground. So first 2 ways is flying with the barometer, either using AGL or AMSL altitude. For those who do not know, AGL stands for above ground level and AMSL stands for above median sea level. So you can see if I go to parameters and show elevation, here you can see that we are currently flying at AGL altitude. So the drone will be flying, it will be kind of following the ground according to the terrain data that is inside of UGCS. Then second way is to fly according to average median sea level. And this will mean that this green line that you're seeing here, instead of it following the terrain, it will simply be straight at the set level. But when we are flying with the GPR, we prefer to use the third method, which is true terrain following. Because with the GPR, you want to be as close to the ground as you possibly can. And this is why in true terrain following, obviously, it will follow the terrain using the data coming from the altimeter. Yeah, the webinar is being recorded. So this webinar recording will be available on YouTube afterwards. So to continue, now, once we have our mission planned, then next thing what we need to do is we need to upload it to our drone. So let's do that. And you can see that our emulator drone simply jumped here. Of course, with a real drone, once you turn the drone on, you would see it somewhere here on the map, and then you would just have to move the first waypoint to the location of where the drone is. Then next, let's move on further to using the custom payload monitor. So in this case, to save us some time, I will simply use the simulation mode on it. It'll kind of simulate the way how a real drone would act, and it will simulate radar data, altimeter data. So let's turn on the simulator mode now, and let's click on start. So here you can see we are seeing green circles here. This means that the custom payload monitor is connected to UGCS. It also means that there is a drone connected and that it is connected to the SkyHub computer. So this is normally the image that you would see before you would start the mission. Then next, here you can see in the altimeter section, it's just now, because it is in simulator mode, it's just kind of randomly generating numbers, I think from 5 up to 35, so it's kind of going up and down. But basically, when you would be using the drone with this, then you would see the actual altimeter reading. So let's say in this case, from the laser altimeter, measure approximately 1 meter from the ground. And then you would set the minimum height and the maximum height. And this does relate to the next section, which is the terrain following. So here in the terrain following section, you would set the target altitude. So for the zoned radar, for instance, you can use a target altitude of, let's say, 1.2 meters, which will mean that the antenna itself, it will be about 60 centimeters from the ground, or 0.7. Then next, you'll be setting the safe altitude. So safe altitude is the altitude to which the drone will go in case it reads a faulty reading from the altimeter. So this means that in case the altimeter reading will be outside of these boundaries, so outside of minimum and maximum boundaries, it will switch to safe altitude and it will go up. And then once it's there, it will simply hold and it will wait for a further command. This is simply to kind of avoid the situation where, let's say, there might be some kind of hole underneath the drone, and the drone might think that, okay, I do need to go down because the altitude suddenly is a lot bigger. So this kind of helps you avoid that and helps you keep your system safe. And then finally, we are adding a flight speed. So in most cases, we are using flight speed of about 2 meters per second, but maybe for some smaller areas, you might actually want to be flying a bit slower than that. In this case, I think I'll set that to 2, but in many cases, you can also use 1 meter per second. And down here, this is where you're seeing the data from the GPR. Note that this is not a live data from the GPR. This is simply simulated data in this demonstration. And here you can see, you can switch between seeing one trace and seeing a profile. And essentially, a profile is basically a combination of multiple traces. And so with these settings all put in here, so the main ones are target altitude, safe altitude, and the drone speed. And with mission uploaded, next thing what you do is you click on write, and this writes the settings to the data logger. Then after that, you can click on read, and this will read the settings from the data logger. Then to launch the drone on terrain following mission, all that's left to do is click on auto mode. In this case, since it's an emulator, I will also arm the drone separately. So once the drone is armed, I will switch it to auto mode. And so now I can see the drone is moving up. It will now execute the wait command. And while it's doing that, you would click here on activate. And on a real drone, it would activate the terrain following mode. And then the drone will basically move down to the altitude that you have set here. So to target altitude. So basically this number that it is measuring would match this one. And then it would fly the mission at this altitude and at the speed that you have set here. So this is kind of like a short intro on how to plan the mission here. I think while the drone is flying this, maybe I'll attempt to answer some of your questions that you have regarding this. So I see there's one about the so about what's the maximum altitude at which the GPR can be useful. Well, this does relate to the presentation that I showed you, which basically means that you want to fly as low as possible. In some cases, when you have some bushes or something like that, there's actually an altitude hysteresis inbuilt, which means that the drone might ignore some smaller obstacles that might be in its way. But maximum altitude, I would not really recommend to fly above 5-meter altitude, because already at that, you are losing some quite valuable data. Maybe with some higher frequency antennas, you might fly a bit, with some lower frequency antennas, let's say like the Cobras, you might fly a bit higher, but with the higher frequency antennas like the Zond, you probably want to fly as close as you can to the ground. Regarding how is the antenna affixed to the UAV, as you can see here, basically it is mounted quite rigidly. So it is like moving just a few centimeters, but basically it's not really kind of moving a lot. So yeah, it's quite rigidly affixed there. And in some cases, yeah, you might also actually want to change the angle at which the drone is flying. And I think I will also demonstrate this. So you can see here that as the drone is flying this mission, currently it's basically always facing towards the next waypoint. So at each end of the survey line, the drone is rotating around. And in UGCS, actually, you can make it so that the drone does not change its heading at all. And let me demonstrate you how to do that. So firstly, let's unlock this route, and then let's go to our area scan. So here in the area scan, you see we have a certain direction angle that's set here. This is the angle that we set using this direction arrow. And what you can actually do is you can add a change yaw command, which will change the yaw of the drone according to a certain angle that you specify. So let's say if you want the drone to always face the same way, and if you, let's say, want it to kind of face parallel to the longest survey line, what you can do is that you can take this direction angle, copy it, and then simply put it here. So you can set the drone to this angle with respect to north. And then once it will be flying this mission, it will not really change its heading. And let's demonstrate how to do that. Okay, so now the mission is calculated. Let me disarm the drone. Obviously, you would never disarm a real drone in flight, but since this is an emulator, I will simply speed the process up a bit. So I will disarm it so that once we upload the mission, it will jump to this point, as you can see here. So now the mission is uploaded. Again, I will click on, although of course, normally with turn following, you would click on write, then read, and then you are actually ready to go. So I will click on arm and I will click on auto mode. And now the drone will wait for a few seconds, and as it will start flying the mission, you'll notice that its heading will be parallel to the longest survey line, and even at these ends, it will not really rotate around like it did before. It will simply keep the same heading. So I think I'll show to you this, then I'll show to you how you can do a similar thing, but change it so that the antenna is perpendicular to the survey lines. And then we can probably move on to analyzing some test data. So here, as you can see now, the drone is no longer rotating. And so basically it's keeping a constant heading according to the survey line. So depending on what antenna you're using, it also might change what heading you want to use. So in some cases, you might want the drone to face exactly head on into these survey lines, but in some cases, you might want it to fly at 90 degrees. And I can also demonstrate to you how to do that. So let's again kind of disarm our drone here. And so now what I need to do, I need to change the yaw angle so that it is 90 degrees, basically so that it's shifted 90 degrees. And to do that, I will simply add 90 degrees to this value, which will in turn make the drone rotate. So let's unlock the route and let's see if we can do that. I hope we can set the value larger than 360. Oh, it automatically jumped to 34, and I think that should be fine. So now let's try to upload the mission to the drone. Let's arm it and let's click on auto mode. And of course, now once it takes off, you would click on activate to activate turn following. So then it would go down to the altitude that you have set here under target altitude. Yeah, I see there's some people asking about the presentation. I think, yeah, after this webinar, we'll probably send you the presentation in a PDF format so you can take a look at it. And so here you can see that the drone is now flying in with 90-degree angle with respect to the north. And even when it will reach this end of the survey line, it will still keep the same direction angle and simply move back on the second survey line. This is especially useful for applications such as pipeline monitoring or basically pipeline detection, because in many cases, when you're flying over the pipeline, the antenna needs to be parallel to the pipeline, and so the flight needs to be in perpendicular. But this depends on the antenna that you're using, because for some antennas, such as the Radsis Zone that I have here behind me, for this antenna, actually, the antenna that's kind of inside of it, it is already in perpendicular to the direction of the drone. So when you would be using the Zone 500, for example, for pipeline monitoring or pipeline detection, then you would not really need to rotate the drone like I'm doing now. You'd simply need the drone to keep a constant heading in parallel to the survey lines. With some other radars, such as the Cobra radars, with these, you might want to use something like this, where the drone is kind of shifted 90 degrees with respect to the next waypoint. Okay, and I think, yeah, so I say you're asking for the data from a real flight, and this is exactly what we will do now. So if I show you the presentation, yeah, so basically in our plan, firstly, I just told you a bit about the, how a GPR works, at least, kind of on a high level overview. Then I showed you how you can plan a survey mission using a GPR. And then next, what I'll demonstrate to you is data analysis. So here I will show you basically data from 2 different flights that were done, or 2 different sort of missions, if you will. There are quite a few more flights actually done in these. So the very first one will be pipeline inspection. This was done during the 500 megahertz Zond radar. And then secondly will be the data which we gained in 2018 Greenland expedition, where we found a lost World War II fighter plane. I'll be using two processing software to process the data. One is called Prism2, and the other one is called GeoHammer. So I think we can actually get started. So let's maybe disarm our drone for now. Let's just minimize this. And then now we can move on further to data analysis. So the very first data set I have here, this is from pipeline detection mission. Let me maybe just put it on full screen. So here you can see in the data, this is kind of the raw data that you would get after the flight. So this is not really processed at all, it seems. So the first thing, what you see here are these kind of red lines. So these red lines, these are actually the waypoints. And if I click here on the GPS tracker, so here you can see the GPR trace. And then as you can see, as I'm moving the mouse cursor through the mission, you can see where the mouse cursor is. This corresponds to where the green point is. So you can see if I kind of mouse over one of these red lines, then this is basically the kind of marks that were input there that the GCS data logger put there in the data. So later on, once we are analyzing it, it's kind of easier to tell where are the waypoints, and it's also easier to split this into multiple different profiles. So I'll just demonstrate to you a kind of quick way of how you can process the data using Prism2, and then also I'll show you a way of how you can process the data using GeoHammer. So Prism2 is a more like geotechnical software, but GeoHammer, it's software made by us, which is not really meant to replace geotechnical software. It's mainly kind of meant to maybe serve as an additional tool to quickly be able to analyze the data. So without further ado, let's get into it. So the very first thing that you would normally do is you would remove the background data. So let's do that. And as you can see here, after we removed the background data, kind of these lines that were here, they disappeared. It is possible to filter them out a bit more if you need, but I think for now that should be sufficient. And the kind of second thing what we can do is that we can actually increase the gain. So we can increase the gain in quite a few different places in the data. So we can add some more vertices here to basically expand the regions that we are interested in and to see more data from them. So you can see once we are applying this gain function, you already see these hyperbolas that are here. So these are actually the pipelines. So in this mission, it was flown over sandy soil. And then here, basically there are two gas pipelines that were running through it. If I'm not mistaken, then the diameter of the pipelines was about 0.7 meters. Okay, so again, I'll just say this. If you have some questions, please put them in the Q&A section instead of the chat, so that we are better able to find them and better able to answer them. So any questions should go in the Q&A. Thank you. Okay, so this is kind of after very, very initial data processing that we're doing. Normally, when we're processing the data using Prism, what we also do is we try to split everything into multiple profiles. And then after it is split, then we can kind of take a look at each profile separately. And you can actually split them using the waypoint marks. And then once you split them, you'll kind of see a picture similar to this. And this is where you can basically see the hyperbolas from the pipelines. What material were the pipelines made out of? I think Alex is also here, and I think he'll be able to answer that question. I'm not 100% sure what material were these pipelines made out of. So let's zoom out a bit. Yeah, so like I said, here you can see the hyperbolas from them. One also thing that you always need to change when you are analyzing the flights made with the GPR on the drone is that you need to change the 0 point. So the 0 point kind of matches the altitude of basically the ground level. And the way to do that is that here if you go to output parameters in Prism, so this is where actually the data logger is writing quite a few, basically it's writing information from the flight. So here you can see what antenna was used, you can see what time range was set, how many samples per trace were used, and so on. Also here you can see what terrain following altitude was used. And so this actually allows you to understand at what point do you need to put the 0 point. Oh, yeah, about the pipelines, in this case, the pipelines were made from steel. So basically they are steel pipelines within a sand polygon. So let's expand this a bit like that. And so here also what you can do is you can change the permittivity of this to find out the exact depth of the pipeline. And to do that, firstly, you need to set the permittivity to 1, which is the permittivity of air. Then once you have set that, all you need to do is you need to kind of adjust this time range so that this point, so that the depth of this Bixler maximum point, it's the difference between the antenna and the ground. So in this case, it was about 1.6. So we need to set this to. So you can see now the depth says minus 1.6 meters. So this is actually about where we want our 0 point to be. So next thing what we are doing is that we are basically applying the 0 point. Since we only now have this kind of bigger profile open, then I think I will just apply this to all. And then next thing what you can do is that you can actually change the permittivity of this. And you can set this to the permittivity of the material that these pipelines are in. In this case, for sand, let's actually check what is the permittivity. Let me just quickly take a look at that. Because that's always important. You always need to make sure what material you are flying over. And this will allow you to basically determine at what depth are the pipelines. So yeah, so in this case, it was dry sandy soil. And so for dry sandy soil, the permittivity is set as 3. So let's see, if we set the permittivity here to 3, then we can now try to measure the depth of these pipelines. Also, actually here on the side where it says time in nanoseconds, you can actually switch to depth. So you can see that these pipelines are approximately, at least the top one is about 1.3 meters, and the bottom one seems to be about 2.4 meters. There's a question about measuring the size of the objects using this, and it cannot always be done. But I think once I'll show you the geohammer, then it will make a bit more sense. There's another question about detecting some non-metallic pipelines. It is possible, but in that case, let's say if a pipeline is made out of plastic, you won't be able to detect the pipeline itself, but you'll be able to detect what's inside of the pipeline. So this means that in case when, let's say you have a pipeline with water running through it, then the GPR will be able to detect the water, provided that the pipeline is of sufficient diameter. And this, again, this does depend on the depth. So now I will kind of show you how to do a similar thing using GeoHammer. And I think in many cases, using GeoHammer for some simple data processing is a lot quicker. So I have it open now. So all I need to do is I need to drag the data from the gas pipelines into GeoHammer. Okay, and here you actually can see that we have basically 2 parts on our screen. So firstly, we have the map where you can actually see everything from the top. So here you can see all the, basically here you can see that it is actually sand, like I was telling you. You can actually see the GPR trace. The GPS trace, and here you can see the GPR trace. And here where you see these flags are basically the same kind of red markers what you see here in Prism. So with using GeoHammer, actually it's quite easy to split these profiles, and the best way to do that is by using this tool. So here you can just need to mark the area which you are interested in, and then it will actually automatically split the profiles, and later on you'll be actually able to save them as well. So let me just kind of drag this over here so we have all the data that we need, and so we can remove the rest. So I think we don't really need the data that's on this side at the very end, and also we don't need the data that's over here. So now we can click on crop, and then as you can see, it kind of took away all the necessary parts, so we are only left with our survey lines. So the next part is that I think over here I will, let me move the zoom controls a bit to the side. So here I will remove all of these flags because they are no longer necessary and some of them are missing. So let's do that. Let's click on delete all additional elements. And so now what I will do is I will actually go kind of through this file, and in every place where there is this hyperbola, I will basically put a marker over there. So I think let's go to the very first profile. Yeah, so this is the first profile. And then I can simply double click here. And now it kind of, you see, it places this kind of location mark here. And if I click on this flag here, then it places like a place mark over there. Then on this side, I can do something similar. So it seems like the hyperbola top is approximately somewhere there. Now let's kind of move just through this. So again, in the next part, you can see the pipeline is about somewhere here. Especially, I'm just kind of clicking at the very top of these hyperbolas, and I am placing these markers. And if you're monitoring everything that's happening there on the left side of the screen, that you can actually kind of see, let's maybe hide this. So you can see already we're kind of getting somewhat of a pattern here. So let's just do a few more. Let's try to speed the process up a bit. I think we are almost done with this. Let me just place the few remaining ones, and then we can move on. And I think this is probably the last line that we have. And so as you can see here on this side, we basically in every place where we put the flag on the very top of the hyperbola, if we put all of them together, then you can actually see that kind of roughly here in the middle, this is where the pipeline actually goes. Some might have the question, why are the flags kind of on every second line, the flag is moved a bit? And this is most likely due to the center shift. So basically as the drone is flying, then the antenna is it is a bit at an angle. And so this means that, let's say when it's flying at this first survey line, then maybe the antenna is kind of placed a bit to the back. So it detects the anomaly somewhere over here. And then once it's flying the next survey line, then it's kind of the other way around. So the antenna is pointing at a bit at the other direction, just ever so slightly. And then this kind of makes it move a bit here. And then basically this kind of here where, so in between these flags, this is actually where the pipeline goes. So what you can actually also do using GeoHammer is that you can basically use this kind of highlighting tool to highlight the area where you have the anomaly. And to do that, you can kind of move these arrows over here. And you can see actually as I am moving it, you might not be able to see it as well on this kind of top pipeline, but on the bottom one, you can kind of quite clearly see that there is an anomaly over there. Yeah, and actually, I see there's a question about measuring the size of the objects, and it might be somewhat hard to measure actually the depth of, sorry, not the depth, but the size of the object that might be there. if you are, let's say, if there is some quite a huge object and you are detecting it on multiple survey lines, then you can kind of tell that, okay, there is something a bit bigger over there. In UGCS, we have this function actually of using a double grid pattern. So instead of using a normal area scan, you can enable this double grid option over here. And then you can see basically, as the name applies, it does create a double grid. And as you are flying this with the GPR data, as you're flying with this with the GPR, then later on, once you're doing the data processing, you can actually import the whole double grid over here. And then you can place all the flags according to that. And then basically on using these flag locations or using a prism, you are able to kind of detect the whole area in which you are detecting the object and maybe find some hotspots of it. And that's kind of how you can at least try to approximate the size. But again, that might be somewhat difficult to tell exactly. Let's say it is at least, you know, it is the object exactly at this size. What you might be able to tell, you might be able to tell the minimum size of the object. So let's say you might know what antenna might detect an object at what depth. If I put on this presentation back, so here you can, for instance, see that, let's say if you're using the zone 500 megahertz and you see that the object, let's say it is at a certain depth, then we have a tool that you can use to measure what is the minimum object that you can detect. And so here you can see, for instance, the minimum object that you would actually be able to detect with this antenna in general would be 10 centimeters. So you can say for sure that this anomaly that you're seeing there, it is bigger than 10 centimeters. But how big is it exactly? It might be somewhat hard to be able to tell. So I think this is regarding gas pipeline detection. I think this is it. And then let's move on further to something quite exciting. Let's move on further to analyzing the data from Greenland. So let me put this over there. Let's minimize this. Okay, so I think now at first, same as we did with previous data set, I will at first open it using Prism, and then after that, I will open that using GeoHammer. So to give you a bit of a background, in 2018, we went to Greenland to search for a lost World War II aircraft. And this aircraft was part of the lost squadron, which had to land due to having low fuel. So I think it was sometime in the 40s. So during World War II, they had to land there. Luckily, all the pilots, they survived, so they were picked up, but the planes, they were left over there. Let me see actually if I can pull up some maybe images regarding that. So you have a bit more of a background about that. Okay. So as you can see here, basically, I think this is one of the airplanes that from the lost squadron. So there's quite a few of them that had to land on the ice. So you can see all the propellers are banned, but as I said, luckily everyone survived. So they picked up the pilots, but then they left the planes. And then once they were able, they came back for the planes, but the planes were missing. And so they were simply swallowed by the terrain, which kind of means that they had some layer on top of them. So basically a combination of snow and ice. Initially, they actually tried to look for them using metal detectors, but they underestimated how quickly can the terrain in Greenland change. So I think, yeah, here's the picture of the drone GPR system that we used in 2018. And actually, there were two teams that year. So there were us with the GPR on the drone, and then there was the second team who were using the GPR on the ground. And so actually, we were able to detect the anomaly on the very first, I think it was on the very first survey line actually that we did. So the coordinates of the airplanes was kind of more or less known, but of course you had to confirm to know for sure. And so we kind of found this anomaly using the drone, and then after that, the other team who used the GPR on the ground, then they confirmed that there is indeed something. So let's open up the data and let's have a look at what we saw. So I believe this is the very first flight. Yeah. So you can see June 2018. Okay, so this is the data that you would see initially. Back then, actually, we did not have a few features. We did not have these kind of waypoint markers, these red ones that you saw in other data sets. And also, actually, we did not really have terrain following. So this flight was done according to the barometer, and even in some places it was a bit dangerous because the drone wasn't really following the terrain, and as it was flying, then basically its altitude was dropping. But so this was the initial data that they got after the first flight. So same as we did before. First, you would do background removal on it. Still, you just see a gray picture, nothing really here. And then next is you need to play around with the gain function a bit. Let's just add a few more vertices over here. And so if you expand this region at the very bottom, then you can actually see that there is something here. So let's open up the GPS trace. I think some are missing over here. Yeah, in any case, so here you can see on all three of these survey lines, you are getting some anomaly that's over here. And I think this data already has been processed for the, so the 0 point already has been adjusted and the permittivity as well. Let's check that. It's not really printed here because this is a bit of an older data. But basically here on the side, you can already see the depth. And so it was detected at a depth of a bit more than 100 meters. Normally, if you're flying over soil with the GPR, you probably wouldn't be able to see this deep, but because this was in ideal conditions, so basically it was in snow and ice, so basically this is kind of all glacier ice, then you were able to actually penetrate this deep. So here you can see this is the anomaly, what they initially found. Let's actually see if we can somehow get the trace, the GPS trace over there. So maybe I'll just try to quickly restart Prism. So I think, yeah, this is the data. Yeah, and so you can see here, this is where we have the GPS trace. So let's again do the same thing, just real quick. Let's do background removal on the data. And let's also increase the gain. I can probably add a few more vertices here. So as you would be moving through the data, you would see that as I am somewhere here with the mouse, then you can actually detect that there is an anomaly over here. And then if you're moving a bit further, then you can see actually on the other two survey lines, then kind of roughly in the same point, you are seeing some anomaly. And you know, not knowing the region, it would be quite unusual to to basically have some huge monolith rock over there. So this would be very suspicious, and this would be considered that there might be something there, you know, especially if you're looking for an airplane. I think let's take a look at the same data using GeoHammer. So let's maybe close this up and let's open up GeoHammer. So I'll just gonna drag this the data from the Greenland flight in there. I think we can probably remove the highlighting for now at least. So if we zoom out a bit in the map, so you can simply see where it is. Although these coordinates, they are shifted, so keep that in mind. These aren't the exact ones. Simply so we can make them public. So then regarding the data itself, let's do again background removal on here, and then here you can also actually detect these anomalies right away. So we can try to put markers there, same as we did in the pipeline data. And so here you can again see that it is roughly in the same location. We can actually use this heat map. We can move this a bit lower. I think we first need to move probably this one a bit higher. And then we can use this one to move all of them a bit lower. Yes, here you can detect that there is something over there. And I think so after they detected this anomaly, they did quite a few more flights over the area. I think they should be able to make a double grid to show to you. So let's see. I think then, if I'm not mistaken, then in the next data, they tried a different area. Yeah, I think this might be the right one. I think there's like 5 data sets here. Yeah, so here you can see this is where the double grid is. So this is what was, after you can determine that there is some anomaly, after this, they did quite a few more flights. Basically, they performed the double grid to make sure that if there is something in there indeed. So let's just do background removal, and then you can kind of see here that we again have our anomalies. So let's maybe zoom in a bit on them. Maybe we can adjust the gain a bit to contrast. I think like this it might look a bit better. And then basically what you can do is same like I did before, you can place these flags. Although I think this is the very first point, so probably not there. And so here it seems to be a bit stronger. So you can see as I will be placing these marks, I will get kind of somewhat of a cluster of these points. Because keep in mind that even once you detect some anomaly, then these coordinates, they might be slightly shifted. So actually what happened was that when they had to drill to make sure that the airplane was there, then if I'm not mistaken, then they had to make like, they found it on the 3rd or the 4th drilling. So I think the first 3, yeah, they did not really hit the target, but on the 3rd or the 4th drill, then they managed to get hydraulic fluid out of it. And that's kind of how they confirmed that it was indeed an aircraft. Oh yeah, there's a question about these kind of lines. So are they snow or just noise? So basically, at least how we interpret that is that at the very top here in the data, this is most likely where you have somewhat of a layer of snow. So it's, it's at some points it's thicker, at some points it's a bit thinner. I think it was actually a bit better seen in Prism, but okay, I think this can also help. So you can see that in some places it is a bit thicker, in some places not. And then down here, this basically just seems to be a huge layer of ice. Later on, I'll show you some pictures from when they extracted one other plane from the same place. And then also, basically, it's just like a solid layer of very thick layer of ice. And they just had to melt down through it. And so then basically, as you are moving through this data, once you detect some anomaly, you can make more flights using the double grid. And then this is how you can add more waypoint markers and kind of create a cluster around the anomaly, and kind of where you have the center point of it. This is likely where by digging or drilling, you might find the object. There's a question about has the plane been recovered? So this plane has not been recovered. From what I know, they are still gathering some finances, some investments for doing that. But there's quite a good story of another plane that's from the same squadron that was also landed there. And I think it was in the 90s that they found it. And then they basically, what they did was that they melted these kind of huge tunnels for people to climb down to the airplane. As you can see here, I'm not sure if there's going to be an image of one of the holes. Oh, there it is. So here you can see there's a person kind of rappelling down the hole of ice that was melted. And so what they did is that they actually disassembled this airplane in parts, and then they brought it up by parts. I think here you can see where it's already slightly disassembled. I think the engine is, one of the engines is still there. So basically then they brought it up, then they brought it to the United States, and that's where when they restored it. And so now it's actually currently in flying condition, and they renamed it the Glacial Girl. So it's quite an interesting story. Yeah, seems like this is already after they restored it. So here you can see when the plane's already flying. So I think that's kind of it regarding data processing. And so I think from this expedition, everything should be kind of clear. So basically, I showed you two data sets. One was from the pipeline detection. The other one was from looking at basically detecting the airplane in the 2018 Greenland expedition. So we used two programs here. One was PRISM2 and the other one was GeoHammer. So PRISM2 is provided together with the radars themselves. It's made by Radsys, actually, so the company in Latvia. And then there is the GeoHammer. It's a software made by us, but this isn't really intended to replace traditional geotechnical software. So I think we can now actually proceed on further to some Q&A, and then we should be done. So here I managed to cover most of it. Yep. So I think let's now do a Q&A, and I can maybe show you some more kind of parts of UGCS. If you want me to, I can maybe try to explain a bit more about GPRs, and let's see what questions you have. But again, keep in mind that regarding GPRs, you do need to have a geophysicist ideally with you. I do not claim to be one. I'm not a geophysicist myself. So for quite detailed GPR questions, you do still need to consult specialists. I can basically, what I can help you with is with answering drone GPR related questions mainly. So let's see. There's some questions about the costs of the antennas. I think these our sales person Oscars will try to answer to you directly. So I can say that actually the Radsys antennas, they're quite a bit cheaper than the Cobra antennas. And I know that they have a Cobra CBD that's called, and it's actually quite similar to the Zond 500. So I think for most applications that do not involve where it's not necessary to see quite deep underneath the ground, actually it might be sufficient to use a Radsys Zond. If you want to use the GPR, let's say for some geotechnical applications, so let's say maybe detecting some underground caves, tunnels, then actually probably the Cobras might be a bit more suitable for that. So there's a question, is there a way to maintain constant vertical when the terrain is rugged? There is a way to do that, and basically there are two main ways, I'd say. One way is to actually fly a bit, and this is one assuming the terrain is like really, really rugged and that the drone would kind of struggle to keep a constant altitude. So in these cases, you can actually kind of fly at an AMSL altitude, but then keep in mind you do need to be a bit higher, and then you might lose some of the data. If you are using a lower frequency antenna, this might be suitable. So in those cases, you might simply fly at an AMSL altitude without terrain following, and you would still gather some useful data. If you would be using an antenna with a higher center frequency, such as the Radsys Zond 500, with this you want to be quite close to the ground. And so what you can do here is actually you can use our terrain following, but together with it, inside of the data logger, you will actually have the ability to set altitude hysteresis. So this means that you can actually change it to not take into account any changes in like a certain kind of either a certain distance or in a certain percentage. Let's see if I can maybe use Zoom to, let's try to do some annotations here. Yep, I think this should work. So for example, if we assume that the terrain is moving somehow like this, then let's switch to green here. Or maybe let's see some other color. And then we can say, okay, so if the drone would be flying normally in terrain following, then it might fly somehow like this. However, if you wanted to fly a bit more constantly, what you can do is you can change the hysteresis. So there's two ways of doing that. First way is that you can set it in relative terms, and second way is that you can set it in absolute terms. When you're setting it in absolute terms, then you can simply specify the maximum hysteresis in meters. So let's say you can specify the hysteresis to be 1 meter. So this means that the drone won't take into account that many changes in the elevation, and so it will not really kind of move as much as the terrain level is moving. And second way is you can set it to relative, and this means that you can set a certain percentage of the measured altitude that it will kind of use as for the hysteresis. But in any case, the end result is that it will not kind of move as much and will be flying over rugged terrain, or especially if there's like some bushes here, then also that might help. Of course, keep in mind that you do need to maintain a safe altitude above ground. One thing about the GeoHammer software, actually, what I can mention is that the GeoHammer software is actually available freely. So we are not charging for it. And actually, if you go to our GitHub, then you would be able to find it. So simply Google GitHub UGCS. Then you can go here. And then here you can see UGCS GeoHammer. So you can simply go here. Then you can go to releases, and then you can actually download our GeoHammer software, play around with it. It accepts the standard GPR data, which is SGY. Yeah, so I see another question from Andrea. Yeah, so yes, when you're using a GPR on a drone, it does lose a bit in the kind of the penetration depth. This is also because of how the beam kind of travels through the air. So it does get a bit kind of dissipated, so to say, and the higher you go, the less kind of you will see from the data. So for example, if you would be flying, let's say at 10 meters with the zoned radar, you probably wouldn't really be able to see anything. So you always want to be as close to the ground as you can. Yeah, so from David, I see there's a question of how does UGCS deal with tall objects encountered during the flight and avoiding collision when close to the ground? This is actually quite a good question. So firstly, let's kind of try to put two separate things. So firstly, there are some, let's say, man-made objects or some trees. So let's imagine, I think over here, yeah, here we have some trees. So trees, cars, buildings, and so on. With this, there is no really there's no avoidance on the drone itself, unless, of course, it has these sensors around it for obstacle detection. So in these cases, simply as the operator, you need to make sure that there are not any obstacles nearby. What you can do is you can actually scan the area, perform a photogrammetry mission over it, and this will also allow you to see if there are any obstacles or not. But in most cases, you always need to be aware if there is anything. Regarding let's say regarding ground elevation, so if in some cases, for instance, the ground might go a bit higher or might go a bit lower, this actually does relate to the speed at which you are performing the survey. So as an example, if you have quite a steep mountain, let me try to see if I can annotate it here. So if you have quite a steep mountain, then you might not be wanting to fly at 3 meters per second. So in this case, it might be better to fly at 2 meters per second, because you see, it still takes some time for the drone to adjust its altitude based on the readings from the altimeter. So let's say if you have it set at 3 meters per second, then it will be kind of flying at this speed. And as the slope approaches, it will kind of gradually, it will still attempt to climb, but it will kind of get closer and closer and closer if it's flying too fast. However, if it is flying a bit slower, let's say this will be at 2 meters, so then it will not kind of approach it that fast. It will have time to react upon these changes, and so this will be a bit safer. Another example might be when, let's say, you might have some kind of terrain that's going like this, so it's kind of more or less flat. Then suddenly you have like a bigger hole that's over here, and then again, it's somewhat flat. So in these cases, when you are flying, what's kind of happening is this kind of minimum and maximum altimeter reading settings, these are what come into play here. So let's say if you have the maximum altimeter reading, let's say set at, for instance, let's say 3 meters. So if the drone will be flying like this, let's say here, let's assume the altitude is like, let's say 1.5 meters. So then as it would reach this point, at first it was going to still attempt to go down a bit. And then suddenly this reading, would increase. So let's say here, the reading might be 4 meters. So if here the reading would be 4 meters, which would be more than this 3 meters that you would have set here, then what would happen is that the drone would go into terrain following failsafe. This means that the drone would go up to the safe altitude that is set over here. So in this case, you can see it's set to 10 meters. So it will go here and it would hover waiting for your further commands. So you can either reactivate terrain following, and then that would make the drone go down, or you can also actually manually control it. So you can control it a bit lower and continue the mission, or you can even fly it a bit further and also continue the mission. So let's see what other questions you might have. Well, I'm just going to scroll through them a bit. If you are interested in some test data from the GPR, so either from the GPR on the ground or the GPR on the drone, then you can reach out to us directly. There is the email. Let me just put it over. Let's put it over here. So firstly, we have UGCS at UGCS email. This is what you can also use. Or we have our industrial website. And so on this website also, you will have our contacts, or you can contact all our salesperson, Oscars, directly. And then this is how we can provide you with some sample data if you want to take a look at them. And also, of course, we can provide you with the prices of the antennas as well as the price for our system. Yep. So it's important maybe to know that together with the system, what we'll provide is firstly all the components you see behind me. So this would be except of course the drone. So we can provide the radars, we can provide the data logger, the laser altimeter, as well as the software. And together with that, actually, we also provide the training. So once you get the whole system, we'll kind of teach you how to use it, teach you how to set it up. So this is all documented, and we will kind of help you through the whole process so you can get started with performing GPR drone flights. And see, there's some questions about will the Q&As be available? Let's see, I'm not sure if we'll make them public, but the webinar itself, the recording will be available. And if you have some specific questions, then we can kind of answer them to you directly, or you can simply reach out to us. Yep, there was also a question of what is the live data that you'll be seeing here. So from the radar, firstly, here in the custom payload monitor, you'll be seeing the trace as well as the profile. This is just kind of randomly generated. In this case, since I'm using a simulator for a real drone, you will see the real data coming here. But still, from this data, you would not kind of be able to tell that much other than there is some data coming. And maybe if there's some bigger obstacle, you might be able to see it here. But the general idea is that after you perform the flight, once you land with the drone, then using the custom payload monitor, you can actually download the data. So if you go here and then go to, let's open up tools. Essentially here, once you are connected to the Wi-Fi of the data logger, then here you can simply click on download. It will download the GPR data file straight to your computer, and then you can start analyzing them. Yeah, another question is, how does the GPR react to water bodies, so small rivers or ponds? This is actually one of the applications of GPRs. We have actually a sample data set from when we did bathymetry over lakes in Denmark. So as long as it's freshwater and not saltwater, then you can actually use a GPR to perform a bathymetry survey. And even from this, actually, what you can do is you can reconstruct a 3D model of that in many cases. Let's see if I have it here. So yeah, if you go here in the presentation to applications, I think it was somewhere here. Yeah. So yeah, here you can see you can use GPRs for bathymetry of lakes and rivers. Normally, you can use it using a boat. So when we were in Denmark, actually, we were doing it in multiple ways. So firstly, we were performing the survey simply by putting the GPR on the side of the boat and then going with the boat through the lake, simply scanning it like that. and that took forever. And another way, of course, is that you can simply put the GPR on the drone itself, and then you can simply launch it on an automated mission, which is way easier. And this is actually also one of the reasons why we implemented or why we added the radar altimeter, because the laser altimeter doesn't always work perfectly over water. So this is why we switched to using radar altimeter. So in cases when you are using it for bathymetry, then the radar altimeter can work a lot better. And so the drone will be able to kind of smoothly glide over the water surface at the set altitude. So, okay, I believe I have answered most of your questions. So if you have some other questions, then simply send that to us to ugcs@ugcs.com, or contact us also through our website, industrial.ugcs.com. Thank you so much for joining this webinar. I hope it was useful for you. I hope you learned something new. And yep, let's stay in touch. And oh yeah, so regarding the Q&A that a few have asked about, I just got the answer that we will publish the Q&A after the webinar. So after this, you will be able to see it. Yeah, so thank you so much, everybody, for joining. I think that's it for today, and I hope to see you in future webinars.